This video will cover static routing. There are two ways in which remote networks can be put into the routing table on a router. Either manually, which means you're going to enter them in by yourself through static routes, or dynamically, which means they're going to be learned automatically through some type of dynamic routing protocol, such as RIP, OSPF, or EIGRP. Why should we use static routing? Well, static routing does provide some advantages over our dynamic routing. Static routes are not advertised over the network, so this results in better security. There are going to be no packets that could be sniffed containing routing protocol information. Static routes use less bandwidth than dynamic routing protocols. There is no CPU used to calculate and communicate the routes like there are in dynamic routing protocols. And with static routing, we know for sure the path that a packet is going to take to get from one destination to the next, because we manually put that in there and we get to control and decide which path that packet will take. There are some disadvantages to static routing. The initial configuration and maintenance can be very time consuming. If you have a very large topology with many subnets, typing in all of the routes to all of those different subnets is going to take a while. The configuration is error prone. Because you are manually entering these in there, all it takes is entering in the wrong outgoing interface or entering in the wrong subnet mask, and we're going to have errors on our network. If we want to change the route packets take to get from one destination to the next because of a link failure or something, we have to go in there and manually change that, so it does require some administrator intervention. It does not scale well for growing networks. The maintenance can be cumbersome. It does require complete knowledge of the whole network for proper implementation. It's nice to have a working, complete topology map of your network when setting up your static routes. We'll most often see our static routes when we're connecting to a specific network, when we're trying to provide a gateway of last resort for a stub network. We want to try to reduce the size of the routing table by summarizing several contiguous networks, or when we want to create a backup route in case a primary route link fails. The first type we'll talk about is standard static routes. These are routes that we see all the time. They're used when connecting from one network to another, and we'll often see them when we're connecting to a stub network. A stub network is a network that only has one way out to reach another destination. Here's an example here where R1 is considered a stub router. If we take a look at R1, he only has one other way in which he can get to any other network, and that would be out of his serial 0/0/0. His gigabit Ethernet 0/0 connects him to his LAN, and if he wanted to get outside of that LAN again, there's only one other way in which he can do that. So that's why it's considered a stub network. So oftentimes we will see static routes set up on a stub router. So for R1, we would probably set up either a default route, which we'll talk about later, to get to R2 and that other network, or we could set up a standard static route to explicitly connect to that one specific network that it's connected to. To configure our standard static routes, the basic syntax is IP route, the network we want to get to with its subnet mask, and then either the outgoing interface to get to that network or the IP address of the next hop. And it really doesn't matter which way you choose. They used to suggest that you chose the outgoing interface. That way we didn't have to do another lookup to see which interface to send out of to get to the next hop address. But as I said, either way will work, and you can actually do both if you want. So as I said, we can either use that exit interface or the next hop. And the next hop can be identified by the IP address, exit interface, or both. How the destination is specified creates one of the following three route types. We either have the next hop route. This is only the next hop IP address is specified. So you would list the next closest interface of the next closest router's IP address for that next hop route. The directly connected static route, only the router's exit interface is specified. So if I want to get from one network to the next, I specify the interface on my router that I send out of. Or we can have the fully specified static route, which actually includes both. We list the next hop address and the exit interface. Here are a few examples. On the left-hand side, we're using the next hop address example, and on the right-hand side there, we're using the exit interface. My preference is to use the exit interface. I just think it's a little bit easier, and as I said, they both work the same. But let's take a look here at this example. We have R1, and the only networks he could currently get to would be the 172.16.3.0 because it's directly connected to him. And he could also get to the 172.16.2.0 because it's directly connected to him here. He would not be able to get up to this 10, down to this 192.168.10, or to this 192.168.2.0. So he would need routes to this network, and this network up here. Otherwise, he would not be able to deliver traffic to it. So what we type in here is in global configuration, we type IP route, the network we want to get to, 172.16.1.0 with its subnet mask, 222.55.0, and then the next hop address. So R1 says that I can get up to this network up here by sending to the next hop address of this, 172.16.2.2. So we're going to send that up to router 2's serial 000. And that's all we can do with our routing is get it to the next hop, and then we hope that he can deliver it. He would then look in his table and he would see, oh yeah, that 172.16.1.0, he's directly connected to me. I can go ahead and I can deliver it to that network. Same thing to get to that network over here using the exit interface, IP route, 172.16.1.0, 222.55.0. But instead of the next hop, we specify serial 0/0/0. We're specifying the interface we're sending out of locally here to get to the next hop. So we're going to send out of our serial 0/0/0. Again, either way will work. It's up to you on your preference which one you want to use. IP version 6 is no different. With IP version 6, instead of doing an IP route, we type IPv6 route, the destination network, and then either the next hop address, or we can use the outgoing interface. So same thing here. Let's look at this example with router 1. We do an IPv6 route 2001 db8 ACAD 2::64. What we're typing in R1 here is a route to get up to this network. We are specifying this network address, and then we're specifying the next hop that we would send to get to it. And we're specifying this address right here, 2001 db8 ACAD 4::2. And here that is, 2001 db8 ACAD 4::2. I'll just pick a random one here that does not have an example listed. I'll pretend that R2 needs a route over here to this 2001 db8 ACAD 1::64. So what I would type in there on router 2 to get to that network would be IPv6 route 2001 db8 ACAD 1::64. And then in order for R2 to get over to this network, he would send out of his serial 0/0/0. Default static routes. We see these quite often. A default route is a static route that matches all packets. Rather than storing all routes to all networks in a routing table, a router can store just a single default route to represent any network that is not in the routing table. A default route is used in the table when no other matches are found for the destination. So instead of dropping a packet, if the network is not in the routing table, it can use the default route instead, but only if that default route exists. This is commonly used when we're connecting an edge router to a service provider network, like the internet, or a stub router, as we had in that very first example, to get to his upstream neighbor. So a very common scenario where I may see a default route is in a situation where I have a router connecting to a local area network here. Just draw a switch here quick. And then I would have my PCs connecting into that switch. Or maybe it's a wireless PC connecting into a wireless access point or whatever it happens to be. Or maybe this is your home network, you have a wireless router here, and all of your PCs are connecting wireless up to that wireless router. And then you have the internet. This is my cloud, connecting to that wireless network. Well, it would be impossible for you to go to this router and type in every route to every network on the internet. If you wanted to get to Google, Google's on a 74 network. And if you wanted to get to Yahoo, Yahoo's on a 209 network. And every single website and place you go to the internet, you would have to have a route to get to that network. Well, that's not very feasible. So instead what we do is we enter a default route. And what that default route says is anything that's not in my table, match my default route and send it out of this interface to get up to the internet. So we see that quite often when we're connecting to a service provider, an internet service provider is. We just put a default route in here to get it out to the internet, and then once we're on the internet, we can get the traffic delivered to where it needs to be. Again, it would be impossible for us to try to maintain a route to every single network on the internet. So instead we can just use that default route. So to configure that default static route, we use the quad 0. We do an IP route quad 0 space quad 0, and then again either the next hop address or the outgoing interface or both. So here's an example with R1. We type in IP route quad 0 quad 0 172.16.2.2, or we could replace that 172.16.2.2 with the outgoing interface of serial 0/0/0. So now how this default route is used is any traffic that hits R1 that it does not have a specific route for will meet this default route or gateway of last resort, as it's also called. So if he got a packet that was destined for the 192.168.2.0 network that would hit R1, R1 would look for a specific route to the 192.168.2.0. He wouldn't have one. He sees this default route or gateway of last resort, and he would then send it up to the next hop of 172.16.2.2. R2 would now get that packet, and R2 would look for a specific route to the 192.168.2.0. And if he had one, he would then send it to R3. If he did not have one, he would look for a gateway of last resort and see where that told him to send it. If a gateway of last resort or default route was not set, he would then drop the packet. Also, any network that's not in this topology would also meet this default route. So if R1 got a route for the 10.10.10.0 network, it would also meet this criteria, and that packet would then get sent up to R2, and we would see if R2 could deliver that packet that's destined for the 10.10.10.0 network. For IPv6, not a whole lot changed here. You do an IPv6 route. We do a :/0 instead of the quad 0. So this is where the change comes in here. The :/0 is the address that will meet any network that's not in our table. And then here they're doing a next hop address, which in this example would send it up to R2's serial 0/0/0. Another type of static route is a floating static route. Think of a floating static route as a backup route. What makes it a floating static route is the fact that it has an administrative distance greater than the administrative distance of another static route or a dynamic route. Remember that the administrative distance is the trustworthiness of the source of a route. For example, a directly connected network has an administrative distance of 0. It does not get any better than being directly connected to that network. A static route has an administrative distance of 1. An EIGRP route has an administrative distance of 90. OSPF is 110, and RIP is 120. So as long as that static route has an administrative distance that is greater than the current route, it will become a floating static route or a backup route. We use the term floating because the static route floats and is not used until that route with a better administrative distance happens to go down. In order to configure a floating static route, we use our basic syntax of IP route, the network we want to get to, the subnet mask of the network we want to get to, then the next hop using either the outgoing interface or the next hop address, and then we add the administrative distance onto here. So in this example, R1, we have a default route up to router 2. So any traffic to a remote network that R1 gets is automatically going to be sent up to R2. We then enter in a floating static route that sends any traffic to a remote network to R3, but we set it as a floating static route. So what that means is this is going to become just a backup route. This route up here has an administrative distance of 1, and this static route down here has an administrative distance of 5 that we set. So this administrative distance of 5 is worse than our current administrative distance. So this route down here does not get installed into the routing table. So how traffic is going to be routed in this network is everything gets sent up to R2, and then we hope R2 can send it around the network. In the event that R2 goes down or this link goes down here, our backup route or our floating route will now kick in. We will now be able to send packets across this link along the bottom to R3. So with our floating static routes or our backup routes, they are only used if the better route that's currently installed is unavailable. So we see this a lot when we have backup routes that we only want to use when the main route is down. One thing that we can do with our routes is summarize a bunch of networks into one. When we summarize these networks into one, this is often known as supernetting or CIDR. The networks that we summarize together must be contiguous. To calculate a summary route for IP version 4, what we must do is convert all addresses that we want to summarize into binary. So in this example here, we're going to summarize the 172.20, 172.21, 172.22, and the 172.23 networks all into one summary route. So we convert them all into binary. Once we have them converted into binary, we find out how many digits starting on the left-hand side match. And in this example, there are 14 digits that match. We can see here that at the 15th digit, they start to change. But these first 14 are all the same. As soon as they start to change, then we do not count up any other matching digits. So it's from left to right, the number of matching digits. And the next example, it's 14. The number of matching digits becomes our new subnet mask. So we had 14 matching digits. Our new subnet mask is a /14, which is 255.252.0.0. So once we have our new subnet mask, we need to determine the new network address. So what we do is we draw a line where those numbers stop to match, and we make the right-hand side all zeros. We convert that back into decimal, and this gives us our network address. So the digits that matched were 172.20. The rest is 0.0. So our new summary address is 172.20.0.0 with a /14. So we were able to summarize these four networks into one supernet, or into one network of 172.20.0.0 with a 255.252.0.0. So here's another example where they summarize the 172.16.10, 20, and 30 networks into one. So again, what you do is you convert all of these into binary, you find out where they start to differ, and figure out how many digits are the same. And in this example, there happens to be 22 digits that are the same. That 22 becomes our new subnet mask. In this example, it's a 255.252.0. We then take the digits that matched, draw our line here, make the right-hand side all zeros, and convert back into decimal. So when we convert this number back into decimal, it's 172.16.0.0. So we're able to summarize the 1020 and 30 networks into 172.16.0.0 with a /22. We can summarize IP version 6 as well. It's essentially the same process, but we do have a little bit more to do since we're working with hexadecimal instead of decimals. So we have a few extra steps that we need to do the hex conversion. So to calculate an IP version 6 summary route, what we need to do is figure out where the addresses differ again. And in this example, where they start to differ is in this hextet here. They're all the same until we get to the 1, 2, 3, and 4. Then what we do is in the hextet where they differ, we convert this to binary. So when we convert this into binary, that hextet, it's right here. Remember that each hextet is made up of 16 binary digits. We then count up the number of bits that are the same, and this becomes our new prefix. So in this example here, we have 61 bits that are the same. Remember, each hextet is 16. So here's 16 bits, here's another 16 bits, here's another 16 bits, and here's 13 bits that are the same. So our new prefix is a /61. We then do the same thing that we did with IP version 4, convert that whole right-hand side to all zeros, convert it back, in this case to hexadecimal, and that's our new network address. So in this example, all 4 of these networks summarize to the 2001 DB8 ACAD :0:/61. There are some more examples in the curriculum on this section for IP version 4 and IP version 6 summary route calculations. I encourage you to take a look at those to get some extra practice with it. This slide here shows an IPv6 summary route address in action. The first thing that they do is they take out all of the single static routes that they had in for R1. So R1 had static routes to all of these remote networks. And what we decided to do, instead of having each one in there individually, is summarize all 4 of these into one. So we take out all the individual ones by doing the no IPv6 route and what the route was. And then we put in the summary route by doing IPv6 route, what the summary route was with the summary prefix. And then here they're using the next hop address. If you're having problems with your static routes, there are a few commands that we can use to troubleshoot and to verify. We can use the show IP route, we can use the show IP route static, or the show IP route in the specific network that we're looking for. The same is true for IPv6. We just changed the IP with IPv6. So show IPv6 route, show IPv6 route static, and show IPv6 route the network that we're looking for. One very common mistake that I see a lot of students make is when they do their IP route statement, they do the IP route to a specific PC instead of the network address. So they might do an IP route 192.168.1.1.225.5.0 out the serial 0. Well, in that statement, you're only specifying a route to one specific PC. Instead, we want to specify the whole entire network. We want to do an IP route 192.168.1.0 with the 222.5.5.0, and that will specify all addresses in that 192.168.1.0 network. So be on the lookout for that when you're entering in these static routes as well. That's all for this video on static routing. Thanks for watching.